Okay, good morning, everyone. Today we begin chapter 3, diodes. That's the first of the semiconductor device that we will study in this class. Class notebook. Okay, so my plan is we first look at what a p-n junction is, some of the electrostatics, what happens when you bring a p and n-type semiconductor together, the interactions between the charge carriers that takes place at the junction. And then we'll go into the circuits, the different kinds of circuits that we can create using diodes. And I estimate we'll spend at least 2 weeks, if not more, on this topic. Okay, and Zener, not including Zener diodes, so exclusively diodes and diode circuits. So let's first take a look at what happens when you have a P and an N-type semiconductor in contact. Now, this is a typical illustration that has been in use for several decades. But typically, this is not how we create devices. We don't create a p-type semiconductor separately and an n-type separately and then glue them together, right? Even though the model makes it seem like that. Okay. If you all recall from last class, we talked a little bit about IC fabrication or semiconductor fabrication, where you'd have either a P or an N-type material, right? And then you would create the opposite material inside that material. And that is how it's typically done. Again, the model the illustration here makes it seem as if we create the two materials separately and then join them together. That's not how it's made. Anyway, so we have the p-type material on the left, n-type material on the right. The junction between the two, where it's in contact, is known as the metallurgical junction. Typically, we just refer it to as junction. So it's a metallurgical junction between the P and N-type semiconductors. On the P side, if you have an excess of holes, the subscript notes the type of the material. And so we have PP, meaning the number of holes that are present in the p-type material, and NP, meaning the number of electrons in the p-type material. Okay, these are the number of electrons, and these are the number of holes. Obviously, in a p-type material, the intrinsic minority carriers or the intrinsic carriers are basically the electrons and holes. And then we have a number of acceptor atoms that are implanted or diffused into the material to create a excess of holes. Since holes are the larger number, those are the majority carriers here. And electrons are the minority carriers. On the N side, exactly the opposite takes place. The subscript N refers to the N-type material, and NN is basically the number of electrons that are present in the N-type material, and Pn is the number of holes in the N-type material. And because we have a lot of excess of donor atoms here, these are the majority carriers, electrons, and then the holes are minority carriers, right? The exact opposite. Now, anytime we create a semiconductor device, we need to interface or connect to the outside world. So these devices are very tiny, right? Microscopic scale. And so if you want to make contact, we need two things. Well, first, the size of the contact, and the second is the material property of the contact, meaning how good of a contact the material can make with the semiconductor material. Typically, these are constructed out of some sort of metal. And metal of choice is usually aluminum. there is copper, and there is even gold that can be used to make these contacts. If you ever taken a look at some of these devices or the backside of a CPU, like an Intel or AMD CPU, you'll see that the metal contacts are made out of gold, simply because gold is an excellent conductor of electricity, and it's not affected by the atmosphere as much as other metals. The symbol for a diode is shown right here. It's simply an arrowhead pointing in the direction of the cathode. Also, we have a line or a bar indicating the cathode. Okay, the arrowhead is typically pointing towards the direction of the current flow. If you remember from chapter 1, the first week of class, we talked about diodes, the vacuum tube diode, two electrodes, anode and cathode. And when they created a solid state version of the same device, the naming convention carried over. And so the names were still referred to as anode and cathode. Okay, even though they are not technically electrodes. Oh, and in real life diodes, if you have taken a look at your lab kits, you would have noticed that a real life diode will have a band around that packaging, right? So if it's a typical diode, so in your lab kits, you have both the regular silicon diodes and a Zener diode. The regular silicon diodes in a black epoxy packaging, and so there is a gray band towards one terminal. The gray band indicates the cathode. Basically, it indicates this line right there. The Zener diodes and some other diodes are in transparent plastic packaging. Then you have a black band running towards, running around the packaging towards one terminal, and that again indicates the cathode. Okay, and so the arrowhead and the bar in front of it indicates the cathode terminal. Practically speaking, you can test diode continuity using a multimeter. Most multimeters are capable of testing diodes. If you look at the output terminals, there will be a diode symbol, sometimes a capacitor symbol also, and it means it is capable of testing the diode. You would plug in the diode in a forward bias way in the multimeter, it'll beep, tell you it's working fine. If you connect it in a different direction, positive and negative, it'll be open. Okay, so let's take a look at the electrostatics that occur at the junction. So here, there's an arrow pointing in both directions, actually. For reference, this graph, they are pointing towards the flow of the current, and hence they give a positive direction to the right and a positive direction up. But what this graph is actually showing is this is the junction interface right there. Okay, this is the junction. This is how far deep into the N-type material, or the distance from the junction into the N-type material. And this right here on the left is basically the distance into the P-type material. And that's how you would view this diagram. Again, they're both distances into the junction is in the middle. That's where the P and N-type material make contact. And then on your right is the N-type material, and on your left is the P-type material. So how far into this material the junction is extending. Does that make sense? Right? Now, P-type material, we would assume that the holes are implanted throughout the material. Okay, that's what the assumption is right now. What happens beyond a certain depth, we don't really care. Okay, but for now, we will say that the concentration of the holes in the P-type material is uniform at this level right there. Okay, And then on the N side, the concentration of electrons is constant right there. We don't care about what happens farther away from the junction. Right now, we're only concerned with what happens at the junction. Okay. So excess of holes, these are the majority carriers, and electrons are the minority carriers, indicated by the numbers 10⁻17 atoms per centimeter cube and 10⁻3 atoms per centimeter cube. Again, as a reminder from chapter 2, NP and PN. NP is the number of electrons in a p-type material, is from the intrinsic behavior of the semiconductor, thermal generation, right? They may or may not be implanted in there, but for now, we simply assuming they're simply the intrinsic carrier concentration. There is no implant for N-type, for electrons in a p-type material, and there is no implant of holes in the N-type material. And here you have the electrons are the majority, and holes that are the minority carriers. So the levels are crossing over. What does it mean? What it shows here is, well, actually, when you first had a p-type material, this level would extend all the way to the edge of the p-type material, right? Meaning when they were first brought together at the junction, the number of holes in the p-type material would extend all the way to the edge of the junction. And so would the electrons. But what happens at the junction is there are some effects that takes place. There's a phenomena that takes place. And so we have crossing over of the electrons and the holes. And we'll look at that in the next few slides. And what that does is it results in a gradient. There's a gradient that takes place. Number of holes from the P side are constantly at a high level until they reach close to the junction. Then they drop all the way down to the intrinsic level. As you cross the junction, they are now at a level of the intrinsic concentration on the other side. And the same thing happens with the electrons. The electrons are at a high level on the N side of the junction. And then once it crosses over, it's at the intrinsic level on the P type, on the P side. So there is a gradient that takes place. Okay. It's a high level, and then it gets closer to the junction. The level dies out because there's no more implant of holes or acceptor atoms. And on this side, you have electrons that cross over. Okay, that's what the graph is illustrating. So the junction, there is a gradient in the charge carrier concentration. A concentration of atoms, there is a gradient in the distribution of the concentration of atoms. Now, close contact, yes. No, up is basically just the number of carriers. So this is simply the number of carriers. P is the number of holes and N is the number of electrons. The point about the current was that typically current would be moving in this direction. And so when authors write, or typical convention or accepted convention is, you take the direction of the current as positive while showing this kind of illustration. But what I always like to point out is that X is basically the distance from the junction. So X, N, and XP are basically the distance from the junction into the N and P type material. Okay, so on this side you have XN, and on this side you have XP. Okay. The reason we give a minus to the p side is because it's opposite of the current flow. So let's expand on what happens at that junction, right? We have this junction right here. Let's expand it. What do we see? Across the junction, the holes are higher on the left side, right? Across the junction, there is a gradient in the hole concentration. So holes are higher, the number of holes are higher on the P side, on the left side. And then since they are slowly dying out right here, not dying out, sorry, they are the gradient or the concentration is slowly reducing. There is a gradient in the charge concentration. Chapter 2, phenomena of diffusion. In a bid to create a uniform distribution, the holes will start diffusing from the left side to the right side, meaning from the P-type material towards the N-type material. So holes are diffusing from the P-type material to the N-type material, physically moving, in a bid to create a uniform concentration. Remember, physical quantities always flow from high to low. We talked about two mechanisms of current, right? Diffusion as well as drift. Diffusion is when there is a difference in the concentration of the charge carriers. So holes from the P-type material will diffuse towards the N side. And on the N side, you have an excess of electrons. And so they are diffusing from the N side to the P side. So right at the junction, because there is a gradient, the holes will cross over to the N side and the electrons will cross over to the P side. Let's take a 10-second pause to think over that. Let me know if you have any questions. Any questions? Okay. All right. So diffusion effects take place. Here we have electrons going from N to P, holes going from P to N, and electrons going from N to P. So this gives rise to a current, right? Diffusion current. They're diffusing through the junction, they're crossing the border, and they're going over to the opposite side. You all with me so far? Okay. Now, where did these electrons and holes come from? These are extrinsic carriers due to the implanted impurities. The impurities that were implanted, right? Dopant impurities. Now, these dopant impurities on the N side, we had column 5 elements which had excess of electrons, hence the N-side material. Each of those electrons is balanced by a positive charge in the nucleus of that donor atom. When the electron leaves that local space and goes over to the P-type material, it leaves behind the atom, the ionized atom, which has an extra positive charge. Hence, we see these positively charged ionized atoms on the N side of the material. Make sense? Again, in the N-type material, we have excess of electrons. These electrons are arrived or introduced into the material because we implanted the semiconductor with column 5 elements. Column 5 elements have an excess of electrons, 5 electrons in the outermost orbit. So if it's an excess of electron, that electron is free to move about. But that freedom of movement resulted in the electron moving over to the p-type semiconductor. And when it moves from the n-type to the p-type material, it leaves behind its original atom, its ionized atom, which now has an excess of positive charge. And so you have positively charged ionized donor atoms on the n side. A similar phenomenon takes place on the p-type, on the p side of the material, where the holes crossed over to the n-type material. Because the holes crossed over, these are column 3 elements, and so they now have a negative charge in the ionized atom. And so you now have an excess of negatively charged ionized acceptor atoms on the p-type material. They are localized. They cannot move. These atoms are part of the lattice. They cannot move. The electrons and holes cross over. Thus, the charge carriers, electrons and holes, are now in the other side of the border, the other side of the junction. And because they're on the other side of the junction, there are no more free holes or free electrons in the center area. Okay, so within this, depleted of carriers, depleted of charge carriers, there are no more holes or electrons to conduct electricity. And hence, it gives rise to a region that we refer to as the depletion region, because it is completely devoid or depleted of charge carriers. Electrons from the n-type, holes from the p-type, the other way around. They cross over, they go across the junction on the other side and move into the other material. All right, let's take a pause. Think over that. Let me know if you have any questions. How it would look. Unable to connect. Any questions? Nope. You all with me so far? Okay. So then the next point or the next question would be, if they are actually crossing over the junction, why is that region limited, right? Why does it not extend all the way into the P and the n-type material? Why is it only a small region in the middle right here? Well, so when they first, when I say the researchers, when they first observed this phenomenon, then they were also surprised. And so then the theory would be that if there's a diffusion current taking place, but it's stopping after a certain point, that means there is a competing mechanism or a competing phenomenon that is stopping or balancing out the diffusion phenomenon. Make sense? Otherwise, all the electrons and all the holes would cross over into both p and n-type material, and the and the hole and electron concentration would be completely uniform throughout the entire semiconductor. But that's not what happens. So the theory that was postulated was there must be a competing mechanism to stop or balance out after a certain level is reached. And so what happens is, and keep an eye on this, is that first, because of the concentration gradients, we have the difference in concentration, we have diffusion currents that take place. So the diffusion mechanism gives rise to diffusion currents due to concentration gradients. And then that creates, because of the diffusion of the charge carriers, that creates localized charge density variations. Okay. So there's variation in the charge density. So it's localized variations and the charge density. And because there is difference in the density of charge in different areas, that gives rise to an electric field. And that electric field extends from the p-type to the n-type. Okay, so it extends across the junction. E of x, that is what I marked in the right here. Okay. And because there's an electric field that is acting at the junction, that gives rise to the other phenomenon of drift. Chapter 2 again. And that drift phenomenon gives rise to drift currents, and drift currents will be in opposition to the diffusion current, and both of them will act in opposition until a balance is reached, and that balance is equilibrium. Okay, so this is due E of x, the electric field. And drift current is, of course, the motion of electrons and holes in response to an applied electric field. In this case, we are not applying an external electric field. This electric field is built in. It's self-generated. It's built in. It's self-generated. And then, of course, because they are competing mechanisms, a balance is reached, and the total current after a certain point is zero. So we have p-type material, n-type material, bring it in contact. Diffusion currents arise due to the change in the concentration from the p-type to the n-type. That diffusion current gives rise or creates localized variations in charge density, which gives rise to an electric field. Electric field for acting on the holes and electrons will give rise to drift currents. That drift current is in opposition to the original diffusion current. And then at a certain point, it reaches equilibrium. Total current is zero. Any questions? Let's take a 10-second pause. Does it all make sense so far? Hopefully. Okay. All right. So at what depth would it stop? Right. We just said if there was no competing mechanism, then the diffusion would carry on until the entire semiconductor, the p-type, including the p and n-type material, would be of any uniform concentration of electrons and holes. But that doesn't happen, right? It extends into the n-type and the p-type, and then it stops, right? That region, that depletion region, is not extending all the way. It stops. Where does it stop? Well, that depends on the number of atoms that are implanted. Okay. So depending on the number of atoms that are implanted in both the n-type and the p-type, it'll keep going until an equilibrium condition is reached. Okay. So here, the donor atoms, the number of donor atoms in the n-type material seems to be far less than the number of acceptor atoms that are in the p-type material. Right? Easily visible right there. Na is far larger than Nd. But the equation balances this out. So Q Nd times Xn is equal to Q Na times Xp. xn and xp is the distance of the depletion region into the N and the P-type material. How far does the depletion region extend into both the N-type and the P-type material? And then Xn and Xp put together or accounted together gives you the total depletion region. Make sense? Okay, so again, Xn and Xp, these graphs are always very confusing. When I was a student, I had a hard time understanding what these graphs meant. Okay, it's basically the distance into the P and N type material. So there should be arrows on both ends. So we give a negative, we place a negative in the P side of the equation for us to balance out the equations. Okay, otherwise the equations would never balance out mathematically. The numbers would never even out. That's why I put a negative in there. But X is basically the distance into the semiconductor. So we have XP and we have XN. That's the distance into the semiconductor. So don't forget that. So again, there is a point at which equilibrium will be reached, and the equation right here tells you what the value of Xn and Xp would be. Okay, so it doesn't matter what the donor concentration is, doesn't matter what the acceptor concentration is. They could be of very varying levels, but eventually it will balance out. Okay, that is the property of a p-n junction. That is a property of a p-n junction. If we look at the electric field that is created, again, depending on the number of atoms that are implanted into the N and P-type material, you could have an evenly balanced out electric field or something like this that is shown here. Okay, the maximum value of that electric field will be right at the junction, marked as Emax. Okay, Emax. And because it's an electric field, if we integrate the electric field, we obtain what is known as the junction potential. Basically, the voltage that is present at the junction between Xn and Xp. So right here is the maximum value of that voltage, and right here is the maximum value of the voltage on the P side. So this is known as phi j, the built-in junction potential. There is a built-in voltage that appears across that junction. It is given by phi j. Phi j is simply obtained by integrating the electric field. Okay. Here are the two equations that describe the junction potential and then the depletion region width. Okay. WD0 is the depletion region width, or the width of the depletion region. And as stated earlier, it extends on both sides of the junction. So it's given by Xn, the sum of Xn and Xp, right? The sum of Xn and Xp. All right, Na is the number of acceptor atoms, and this should be Nd. That's a typo I need to fix. Nd. Right, number of acceptor atoms, number of donor atoms. That's phi j. Q is standard unit charge. Epsilon S is the permittivity of silicon. Anybody remember the capacitor equation? Capacitance is given by epsilon A or D. Anyway, epsilon s is given by epsilon r times epsilon 0. Epsilon r is a material property. It describes the relative permittivity of that material with respect to the permittivity of free space. Where epsilon 0, epsilon 0 is a relative permittivity, and epsilon 0 is the absolute permittivity or permittivity of free space. It's a constant, 8.85 into 10 raised to minus 14, or was it minus 18? Minus 14 farads per meter. And relative permittivity for silicon is 11.7. So we'll see that in the next slide where we solve a example. Okay, everything else is a constant. So in this kind of equation, pretty much everything is given. All we have to do is plug and solve. As a real life engineer, if you're trying to actually design something, then everything is a variable, right? NA, ND would be a variable because we need to decide, I need to decide as an engineer, what my implant dosage is going to be. How many atoms do I want to implant in there? That depends on the end result we desire. Okay. But for now, of course, when you're first introduced to the subject, everything is given, a simple plug and solve. So at this point, let's take out our calculators and try to solve this example. Okay. So calculate the built-in potential, the depletion region width, Xn, Xp, and Emax, given that donor atoms and acceptor atoms are 10 raised to 17, 10 raised to 20. We need Ni. Ni for silicon, the intrinsic concentration is 10 raised to 10 atoms per centimeter cube at room temperature. Vt thermal voltage is 25 millivolts. And what else? You need ER, sorry, not ER, epsilon R, which is 11.7. It's a ratio or relative permittivity to the permittivity of free space. Epsilon 0 is 8.85 into 10 raised to minus 14 farads per meter. Please take into account the unit prefix. Okay. Q is 1.6 into 10 raised to minus 19 coulombs. What else? NA/ND or Ni square. All right. So you need to find phi j WD0 Xn XP and Emax. First, find phi j. Yes. Is it? I thought it was always 10 raised to minus 14. Epsilon 0. 10 raised to minus 14. Let me check. No, 10 raised to minus 14. Yep. So let's see. You have everything you need, right? E epsilon S, epsilon R, epsilon 0, Q, Ni. So first step is to calculate phi j. Once you have phi j, then you can enter the value of phi j into WD0. And once we have that, we can calculate Xn and Xp with these equations. Anybody have a value or answer for phi j? Anyone? Any values? No answers yet? Yeah, for phi j. Phi j is no. It's ni square in the denominator. Ni square. Yes, that is correct. Units? Yes. We'll see. So it is 0.979 volts. And then we take that and plug it into the equation for WD0, which is this one right here. 1 plus N, 1 over NA plus 1 over ND times phi j. Do you all get the same answer? How about for WD? Depletion region width? 11.26. The number is correct, but I think the unit prefix merged. So you said 11.26 microns, 10 raised to minus 6. I think you're one magnitude off, I think. So it is WD0. Tier 2, 10 raised to minus 2 off. So it's 0.113 or 0.1126 microns. So it's 2 times epsilon s over q. And let's see, 1.6 10 raised to minus 19, 8.85 10 raised to minus 14 times 11.7 times 2, and then times 1 over 10 raised to 17 plus 1 over 10 raised to 20 times 0.979. Any numbers from anyone else? All right, so it seems as if WD0, depletion region width, is 11.26 microns. Now calculate XN and XP and Emax. 11.249. That was for XP? Oh, okay. What was for XN? 11.251. Okay. Anyone else have these numbers?
I
Anyone
got
else?
the same number for XN, except it's a nanometer instead of micron.
11.251 nanometers. Is that what you're saying?
Yeah, or 11.249 nanometers.
2.249 nanometers. Anyone else? Nanometers? Okay. How about XN? Okay,
Oh, wait,
XN was
the
the nanometer,
XN was the nanometers, yeah.
which kind of makes sense because the donor concentration is very high. So it will not extend too far deep into the N-type material. So XN would be a little bit shallow versus XP. All right, we are actually out of time. Anyone have a value for Emax? Or not quite? That should be a simpler one. 25J divided by WD. So just want to announce there will be a quiz next Monday, right? Let's see. And then, of course, I will post a homework later today, short answer questions and maybe a problem or so similar to this one. And then another homework for the weekend, right? So again, do Emacs and then, well, check the solution. All right, we'll end class here today and pick up here again on Friday.